In this video, we're going to focus on solution stoichiometry. In this course, we'll learn to represent solutions characteristics in terms of concentration. That's the amount of solute, the thing that does the dissolving, per some quantity of either solvent or solution, which is the mixture as a whole. In this case, we're going to focus on the quantity called molarity, abbreviated capital M. Molarity is a measure of the concentration in terms of moles of solute per liter of solution. We can represent this molarity equation as moles of solute divided by volume of solution in liters. We can use this equation to help us move from moles into volume, or to calculate a concentration given moles and volume. We'll focus here on three problems. Firstly, we'd like to know what the molarity of a solution would be if we measured out 17.0 grams of sodium chloride and mixed it with enough water to make 150 total milliliters of solution. In this problem, we know our number of grams of NaCl, and we know our volume of solution in milliliters. We'd like to know molarity. In order to get molarity, we need not grams of the thing that's dissolving, sodium chloride, but moles. We need not milliliters of solution, but liters. So we have two conversions to do before we can plug anything into our molarity equation. 17 grams of sodium chloride can be converted into moles of sodium chloride using the molar mass of NaCl. NaCl contains one sodium, one chlorine. Together, the masses of those elements tally to 58.44 grams per mole. 17 divided by 58.44 gives us to three significant digits, 0.291 moles of NaCl. Separately, converting milliliters of solution into liters of solution requires us to do a simple metric conversion. There are 1,000 milliliters in every 1 liter. That means that we're dealing with 0.1500 liters of solution. To calculate our molarity then, we can just plug into the boxed equation up above. Molarity is equal to moles of solute, that's our sodium chloride, whose mole quantity is 0.291, divided by our volume of solution in liters, 0.1500. Dividing these two out and keeping three significant digits, we end up with 1.94 molar. We'll read the units of molarity as molar, and we'll abbreviate that unit capital M, which means moles of a solute per liter of solution. Therefore, the concentration of sodium chloride in this first solution is 1.94 molar. Suppose instead that, according to our second question, we'd like to make a precisely 2.00 molar solution though. And we'd still like to use the same 17 grams of sodium chloride that we'd measured out in our first problem. If that were the case, what volume of solution in milliliters would be required to make this 2.00 molar solution? So let's reevaluate what we've got for question number 2. We're still dealing with 17 grams worth of sodium chloride, so no need to reinvent a wheel. That's still 0.291 moles worth of sodium chloride. I'm not going to force myself to do that work again. But this time I know a molarity. Molarity is 2 molar concentration. And here I'd like to know a volume, specifically a volume in milliliters. From the equation that's boxed in over at the right, that gives us the relationship between molarity, moles of solute, and liters of solution. we should have everything that we need at this point to solve for liters just by plugging into that equation. Here, in problem number 2, our concentration, or our molarity, is 2.00 molar. Our number of moles of solute is once again 0.291 moles of sodium chloride. But this time we'd like to know a volume. I can rearrange this equation by multiplying both sides by volume and dividing both sides by 2. What I end up with is this, 0.291 divided by 2, which to 3 significant figures gives us 0.146 liters, because volume is measured in liters when we calculate molarity. As one final step, let's convert this volume to milliliters as our question requested. 0.146 liters can be easily converted into milliliters if we once again recall the metric identity. There are 1,000 milliliters in every liter. Multiply through, and we end up with 146 milliliters as our final answer to question number 2. So lastly, and perhaps most practically, suppose that we want to make a solution whose total volume is 1.00 liters and whose final concentration is 2.00 molar from sodium chloride. What mass of sodium chloride would we have to measure out in the laboratory in order to prepare the solution outlined in number 3? For question number 3, we know a molarity and a target volume, and we'd like to figure out a mass of sodium chloride. There's no one equation that relates volume, molarity, and mass together, but we do still have our handy-dandy molarity equation over on the right, which relates at least molarity and volume together, to give us number of moles of a substance. We should at this point be able to recognize that if we can determine moles of a substance, then we can convert that mole quantity into mass later on. So, to approach question number 3, let's, even in doubt, convert to moles. We know that we're dealing with a target concentration for the solution that we'd like to make of 2 molar. That would be equal to the mole quantity of sodium chloride dissolved in the solution divided by the liter volume of solution, which is 1.00 liters. To solve for the number of moles of sodium chloride from this, I'll multiply both sides by 1, and I end up with 2 moles of NaCl. Once I know number of moles of sodium chloride, my solute, I can then convert that into grams of mass quantity of sodium chloride. I'll do that by using the molar mass of NaCl. We've already determined that molar mass to be 58.44 grams per mole, so I can just plug that number in directly. 2 times 58.44 gives us 117 grams of sodium chloride. That would mean that if I wanted to make a solution that's 2 molar in concentration, and I want 1 total liter of volume, then I'm going to have to go into the laboratory and measure out 117 grams of sodium chloride solid and mix it with water to a level of 1 liter. At that point, I'll be confident that I've got a 2 molar solution of this NaCl. So in that last question, we performed a very practical calculation determining what mass of sodium chloride we ought to measure out to mix with water to make a 2 molar solution of sodium chloride. Well, what happens if after you make that solution, you've already measured out 117 total grams of sodium chloride and mixed it up in water to make your 2 molar solution, but then you realize that you misread your recipe and you didn't need a 2 molar solution, you needed a half a molar solution, something whose concentration was 0.500 molar. What do? Do we scrap everything that you just did and start over from scratch? Or is there another alternative? Starting over from scratch means wasting 117 grams worth of sodium chloride. But could we be pragmatic about our approach and take a different route that isn't as wasteful? And not as time-consuming either. Well, there is one alternative. Notice that we'd really like to have a smaller number of moles of sodium chloride per liter of solution than what we've got right now. One way to accomplish this is to take a small fraction of our original solution, the one that was 2 molar in concentration, and add to it more solvent, more water, to increase the volume and consequently increase the space between particles on a microscopic level. That, in effect, reduces the concentration, because while we keep the number of moles constant for solute particles, we're now exposing those constant number of moles of solute particles to a larger volume of solution. This process is known as dilution. And because we can dilute something by adding more solvent to it while keeping the number of moles of solute, like sodium chloride in this case, the same, then effectively what we're saying when we dilute something is that all we're doing is changing concentration by changing volume. Dilution is the process of changing the concentration of a solute by changing the volume of solution that it's in. We have a nice handy-dandy equation that relates dilution for us. Because we know the number of moles is constant, if we dilute something, we haven't changed the amount of sodium chloride that's there, but we have changed the environment that that sodium chloride is in. Then the concentration of our original solution, M1, multiplied by the volume of that original solution, V1, gives us the number of moles of sodium chloride or solute that were present. Because that's constant, no matter what we do to our sodium chloride in terms of adding water or solvent, the number of moles of sodium chloride remains the same. So that means at a new set of conditions, like a new concentration and a new volume, M2 and V2 respectively, we can expect the same total number of moles. That means that the products of molarity and volume at two different conditions of volume must be constant or equal to each other. In this dilution equation, M1 and V1 are the original concentration and original volume respectively, while M2 and V2 are the new concentration and the new volume respectively when we change the amount of solvent or dilute a substance. Every time that we dilute a substance or add more solvent to it, we'll need to apply this dilution equation again. For the question up above, what happens if we really need 1 liter worth of 0.5 molar sodium chloride? What we're referring to up here is a new volume and a new concentration for our sodium chloride. What I'd like to know practically is if we were to go into the lab and draw a certain small fraction of this old solution whose concentration were 2 molar, what volume specifically would we need to draw from that solution, move to a new vessel, and dilute up to 1 liter to accomplish a new concentration of 0.5 molar? In other words, I know an original concentration was 2 molar. A new concentration that we're targeting is 0.5 molar. And the new volume that we'd like that represents that 0.5 molar concentration is 1 liter. What volume, V1, of my original solution will I have to separate out and move to a new vessel and dilute in order to make this new concentration? We can apply the dilution equation to figure that out. our original concentration times our original substance's volume, or aliquot, that we're pulling, is equal to our new concentration, the thing that we're targeting, times the volume that we'd like for that new concentration. To solve for this original volume, we're going to need to divide both sides by 2. When we do, units of molarity cancel, and we'll be left with 0.250 liters. That means that, practically speaking, if I removed 0.250 liters, or 250 milliliters, of my original solution and transferred that 250 milliliters to a new vessel, then just added water until the total volume reaches 1 liter, 1,000 milliliters, then the new concentration of that resulting mixture would be 0.500 molar sodium chloride.